Okay, welcome back. Happy Wednesday. Today we are covering economics applications, more applications that surprisingly are going to lead to integrals. So that's the continued goal. We've got one more brand new topic coming up on Friday, and that one's about probability. That's the last topic before the next test. Monday the 4th is our review day for test number 2, which is coming up Wednesday, a week from today. Okay. The project is due on Monday. Yeah, project 6 is due Monday. Questions on the calendar? Okay, and just one other order of business. I sent an email yesterday, hopefully folks got it, that the homework assignment for the stuff due today was miscopied in the packet. So if you're using the 6th edition, which most of you are, you're going to want to do the homework assignment that's listed in the syllabus, not the one that's in the packet. That's the same for the homework for tonight and the homework for Friday. So every future homework assignment in this packet is referencing the 5th edition instead of the 6th edition. So just go to the syllabus if you have a 6th edition for the next few homework assignments, okay? All right, so let's jump in at the top of page 68. Here we go. Today we use calculus to determine present and future value of money. Just a heads up, the problem number 1 here is not a calculus problem, it's a pre-calculus problem. It's going to warm us up a little bit and then head us into the calculus version of this problem. So without reading that entire paragraph, I'll just tell you that there's a basketball player who is trying to come up with an agreement with his team about salary. In this table, we see 2 options that the team has presented this basketball player. Option number 1 has a signing bonus of $6 million. Each of these numbers is millions of dollars. And in the first year, this basketball player will earn $2 million, and the same thing in year 2, and the same thing in year 3, for a total of how much over the course of the 3 years? $12 million. Not too shabby. In the second row, the signing bonus is $1 million, but then the salary increases 2, 4, and 6 for a total of $13 million. Which one is better? Option 2, because 13 is more than 12, right? My 4-year-old could tell me that. Is that all there is to the story?
Yeah, but now you only start off with 1 million and 6 million.
Yeah, the beginning, the signing bonus of $6 million gives you $6 million, which you can then invest for 3 years and hopefully turn into something more than $6 million, right? Whereas most of the money comes in later in time in option number 2. So we'll make some assumptions about what the stock market is able to do, but 13 being bigger than 12 isn't the entire story. It's not 12 million today compared to 13 today. It's different times. So let's see if we can figure out which one is better. We'll assume that that we can invest in the stock market, which will pay us 10% per year. And let's do some calculations here. So we know from Precalculus Formula that when we have continuous interest, you guys remember this PERT formula, right? PERT, P stands for principal, E is the magic number E, R is rate, T is time. I'm actually gonna write out the word time here. Can you guys add that up there? It's gonna be, we're gonna have the letter T in a second, meaning something that isn't quite that T right there. So P, E to the R times time. A stands for the value, the future value of your money, right? This formula tells you what your money is going to be worth a certain number of years from today when you put it in the stock market. Yep. Okay, for some reason your book uses the letter B here. I've seen it as A for amount, but let's just call it B. Okay, so that's the formula that we're going to use, and we'll use it repeatedly. So let's do option 1 first. Let's look at the $6 million signing bonus. So the 6 plays the role of principal. 6, E to the R is interest rate, which we're assuming is 10%. Do not put 10 up here. What do we put? 0.10. And now multiplied by time. If we stop at the end of the 3rd year, then how long does that money get to grow? 3 years, right? You get it today, we play basketball for 3 years, and then we'll take a look and see what it's worth, and that formula tells you what it's worth, okay? And then separate from that, we've got the salary, the year 1 salary. Let's assume that we get paid at the end of the 1st year. So this one is going to be, instead of a 6, it's going to be a 2e to the 0.1. And if you get that salary at the end of the first year, how many years does it have to grow until the end of the third year? 2 years, right? So it just has less time to grow. And then the next one is 2e to the 0.1 1 year. And then the last one, 2e to the 0.1 times, yeah, if we follow the pattern, it's a 0. And all of this is just equal to what number? 2, right? Because e to the 0 is just 1. So that's saying, you know, on the last day of the third year, you get a check for $2 million, and it's worth exactly $2 million at that time, which is when we're looking at it. Okay, and so we get all of this money, and we are going to take a look at the future value of all of these things together.
So we're assuming he's gonna invest all of his entire salary.
Correct.
He's actually getting paid like
Okay, 6 and change, so he can.
yeah.
Right. Okay, so we've got Yanni typing this in. We only need one person typing it in. Let's write out the formula for option 2. Same idea. Go ahead and write something quite similar to that. You're just going to change the p's for each of these. And if somebody, once they've written it, could type this guy in. Do we have a final calculation yet or not yet? Okay. Okay, so we just type in carefully, 14.7 million is the future value of option 1, meaning at the end of that third year, all of the money in this guy's bank account will total 14.7, which is of course bigger than the 12 million that he was given because of the growth, right? And the same thing, that 14.2 is bigger than the 13, but ultimately we just care about which one is bigger. And now we really can compare these two things. These are now apples and apples. Okay, 14.7 is better than 14.2. So that first option is better than the second one. Fair? Okay. How about we say, well, I don't want to wait. I don't want to get paid spread out over the course of the next 3 years. I just want you to hand me one check today so that we can then figure out so that it would be worth 14.7 million exactly 3 years from now. And we can answer that question pretty easily by using the same magic formula, that PERT thing over there. So I'll just copy it up here. B equals P e to the R times, and I'm going to try to write the word time up there instead of the letter T. Which one of those letters would be appropriately called present value? It's P, principal, like what you are putting in right now at this particular moment in the present, which means the 14.7 is which letter? Is the B. That's the future value. So let's put 14.7 equals P, which we're going to calculate, e to the 0.1, that's the interest rate. And then the time from the start of this experiment until the 14.7 million is 3 years. And that's an equation we can solve for P. So maybe somebody can type in the solution there, and the rest of us can write the other equation for the other present value. Anybody have the other one for us? Okay, and so these are present values, also comparable. Also, of course, the first option is greater than the second one, right? Again, we're making the same comparison just at different moments in time. So this basketball player could be handed a check today at the start of his contract for 10.89 million. If he puts all of it right in the bank and it grows for 3 years at 10%, it will grow to what number? 14.7. And it's just a whole lot easier to think about those numbers, either the present numbers or the future numbers, than the different moments in time you're getting paid different amounts of money numbers. Fair? Okay. So number 2 just kind of reiterates the formulas that we wrote up above. Again, I'd prefer that each of these T's said time. You'll see why in a minute. I'll just write it on those 2. Everything we're going to be doing is the continuous version, which is the E business. I've just included for completeness the annual compounding 1 plus R to the T version, but we're not going to use that. Everything we'll do here is continuous. If you're really fancy, there was the like R over N formula, which you might remember. We won't be using that one either. Okay, number 3. If we view payments as being discrete, meaning occurring at distinct intervals like every year for 3 years, if we view payments as being discrete, then computing future and present value involves no calculus. That's the problem that we just did. However, for some companies, it makes sense to view income or expenses as continuous, called an income stream. You might say that a company is earning P of T dollars per year. Companies make money every day, right? And in fact, companies might think of making money every hour and every minute and every second. Smaller and smaller amounts of money. At the end of the year, maybe this multi-million-dollar company has $80 million in revenue, but they can look at it as coming in these little tiny chunks, like fractions of pennies all the time, but probably not continuous, right? Sorry, probably not constant. Maybe you've got a lot of fall clothing that you sell, and so fall is your big season, or maybe at Christmas time you make a lot more money than at the rest of the year. And so it's not just a constant stream of money coming in at the same rate, it ebbs and flows with seasons, or depending on what kind of thing you are selling or what service you're providing. So let's take a look at number 4. For example, suppose we open a calculus tutoring business and that we estimate T years after opening our doors, we'll have an income stream given by this formula. P of T is equal to 400 times T plus 1 squared dollars per year. Let's calculate some stuff so that we understand what that formula is really saying. P of 1, just plugging 1 in. 400, 1 plus 1 squared. That's 1,600. Right, 2 squared for $1,600 per year. P of 2. And then P of 10. What is it? What's P of 10? All right, business is booming. That's fantastic. So what does it mean? Does it mean in the first year we made $1,600? Yeah, and what kind of a time span is that $1,600 per year valid for? What is it? Just the first year? But what if we plugged in 1 year and 1 second? Will it still be $1,600 per year? It's going to be really close, but it's going to change, right? That formula, you plug in a different number, you're going to get a different answer. And so that $1,600 per year is just a one snapshot moment in time. It's like saying, right now I'm driving 65 miles an hour, but that gives you no information about what I'm doing a second from now or a second ago. It's probably pretty close to 65, right? But that's just one moment in time. And so it doesn't mean that for the first year we made $1,600. In fact, because that function is increasing, did we make more or less money than $1,600 in that first year? More? Is that right? More? Why?
You're constantly increasing. The area under that curve is going to be less than if it were just a straight line.
Yeah, 1,600 is our maximum income stream for the first year. We were making less than that the entirety of the first year, and yeah, so we made less than 1,600 in that first year. You could do an integral of that function from 0 to 1. That would tell you exactly how much money you made in the first year. That's not what we're after today, but that's what the stream represents, okay? Just at one moment in time, we're making this much money per year, but it's not even valid for a second. It's just at one moment. Okay, so moving on to number 5. How would we find the present value of an income stream of P of T dollars per year, or the future value of an income stream? This 1600 business is complicated. $1,600 per year coming in is complicated because it's only for that one moment in time that it's 1600. A second before, it was a little bit less than 1600 per year, and a second after is a little bit more. And the further complication, I had said that we could find the total revenue for the first year. We said it's just the integral of the formula, right? That's a derivative. So that's how much money comes in the first year. It's decidedly going to be less than $1,600. But it's complicated. If I want to know how much money I actually have at the end of the first year, it's complicated. Because let's assume that as soon as money comes into my wallet, I put it right into my bank and it starts growing for me, yes? The instant I get paid, I'm going to throw it right into my bank. And so that isn't the answer to how much money I have at the end of the first year. That's the revenue. But as soon as it comes in, I'm going to start letting it work for me. And so it's complicated because every penny that comes in instantly gets thrown into the bank, but then how long it has to grow in the bank depends on when it came in. Yes, this is a hard question. This is the calculus version of the basketball player. He got paid at 3 distinct moments in time, plus the signing bonus, I guess, was a 4th moment, right? We're getting paid at every moment, and we are instantly taking that money and throwing it into a bank or a stock market fund. So let's see if we can tackle the calculus version. Here's the idea. We've got an interval of time 0 to m. M was 3 years in the problem that we just did with the basketball player. What we're going to do is take our big time interval, like 3 years, and we're going to chop it up into a lot of little pieces. There is one little piece, but really exaggerated so we can see it. The idea is exactly what Coleman said. If we plugged in a year and a second, it would be pretty darn close to 1600, yes? So we're going to pick a tiny, tiny moment in time and say, hey, the money that came in this period of time is pretty much constant, as long as we make it small, and then we'll just make it smaller and smaller and smaller, so that'll be a better and better assumption. And so if the money comes in and it's constant for that period of time, we're just going to treat it all the same, equal, all $1,600 per year for that 1 second period. Okay, let's give this a shot. We know, what do we know? We know that the future value formula from our pre-calculus and from the previous page was this part. But remember, we're writing the word time there, okay? All right, let's start plugging some of these pieces in. I'll leave a blank space there. E to the R times. What expression represents how much time the money in this red interval gets to grow? T years have already elapsed. How much time is left? Is that M minus T? Yeah, that's the time that's, what's that? The plus delta T is so small, you know, like, yeah, if you get money a year from now and you're growing it for 10 years, then it has 9 years to grow. The money that comes in a second later has almost 9 years to grow. So let's just call it M minus T. That's how much time is left. The P is the only thing we need to plug in. It's just a tiny bit complicated, but once we see it, it's easy. P represents how much money came in, how much money you have to invest. The formula that tells you how much money you have to invest is just named P of T. And so the amount of money coming in at any moment in time, at that particular moment in time, which we're calling T, is just P of T, dollars per year. But it wouldn't be right for us to say $1,600 is what we're investing, because that was $1,600 per year, right? And we only got a tiny fraction of that 1,600 in the second that we are looking at. So do we buy that the amount of money that comes in that period is the $1,600 per year times the number of years that passes? $1,600 per year times a second. That's a small fraction of a year. We buy that? And delta t is exactly the amount of time. It's our name for the amount of time that has passed. And if it helps at all, units maybe we'll clarify. This was dollars per year, and delta t is measured in is time, so it's in years. And the years cancel, and we're just left with dollars that came in that little period of time. Okay, so then all of that goes right over here. P of t delta t. So the principal became this stuff right here. And so that expression right there will give you the future value after, say, 10 years or whatever we're talking about, of the amount of money that came in for that little tiny period of time, that 1 second's worth of money. We took it right away, threw it in the bank, and it grew for us for a certain however much time was left. That formula tells you what it grows to. It's the future value of that little sliver of a penny that we just got, okay? But now I want to look at the future value of all the slivers of pennies over the entire period of time. So we're just going to add up lots of things that look like that. Yes? And adding up lots of things like that turns into what? An integral. Hooray. And it's key that we got that delta t in our expression there, because that becomes what in the integral? dt. Fantastic. So all of that translates, this whole thing comes down in here. P of t is copied, delta t shuffled to the end as a dt, e to the r m minus t is there. Integrating from 0 to m, right? That's the entirety of our time period. Okay, likewise, the formula for present value is another integral. We didn't actually focus on the present value formula. What are the two variables? M is going to be a constant that's given in the problem, like 3 years for the basketball player. T is the variable. Interest will also be given. P of t will be a formula with t's in it. So we didn't focus too much on the present value formula, but if you solve this equation right here for p, which was our present value, e to the rt just goes over there, which would bring upstairs as a negative rt there. So then this expression is the thing that's going to get plugged into our integral, that e to the negative rt is right there. So we're not going to go through the derivation, but it's the same idea. Okay, so how about we take a look at the activities? There are so few of us. Why don't we just do this first one together? We haven't actually done any calculus ones together today. So let's try this guy. Suppose an income stream has a value of that formula. That's our tutoring formula. And we'll suppose that the income comes in and is instantly deposited into a bank that pays 4% interest compounded continuously. The continuous piece is going to be mandatory for all of our calculus problems. That allows us to use our E formulas. So you don't need to take it into account. It's already embedded in the E to the RT formula. So we want the present and future value of the income stream over a period of 10 years. And once we've got an integral written down, we'll just type into our calculator. Okay, so let's give this a shot. I'm a big fan of drawing a diagram here. Starting time value goes at the left. What is it? 0. Ending time value, 10. Arbitrary time value, how about we call it t? And then just a little tiny interval, but really exaggerated t plus delta t, the end of the period, the time period that we're focusing on. Okay, let's give this a shot. The future value of our slice, PE to the R times time. We've written that formula many times today. That's PERT. Let's just pull the pieces apart. P becomes our income stream times what? Times the little delta t. So it's just our income stream up there, 400 t plus 1 squared delta t. Highlight all of that. That is p. Times, continuing with our PERT formula here, e to the what? 0.04, that's our interest rate. And then times time. Could be tempting to put a t up there. What is it? It's what minus? Give me a number, not an m. It's 10 minus t. That's how long that money has to grow. It's already you didn't get it until t years into this experiment. And so it's got 10 minus t years left to grow. And I have no room in which to write this. Let's try e to the 0.04, 10 minus t. There we go. And that's it. That's the future value of the money coming in on that little slice of time. And so then the actual future value for the whole thing, all that stuff goes into a summation and then converts to an integral. In this case, integrating from where to where? 0 to 10. Okay, we'll let one or two people type that in for us. You actually could do this integral by hand. We're not going to spend our time doing it that way today. But for the rest of us who aren't typing, let's do the present value version. So our present value was again a calculus formula. It's on the previous page. It was this guy, b to the negative r times t, which I'll write as time. Okay, so that's our starting pre-calculus formula, which will lead us to our calculus thing, technically speaking. Okay, B is just the future value, the value of the thing when you get it. The B, I haven't written this before, but it's the same highlighted thing. Like you're talking about the money on that little interval, and we are grabbing that money when it comes in. 400 t plus 1 squared delta t. I will highlight maybe in another color here. That is that. B stands for future value. From the perspective of 0, starting the experiment right now, the money coming in t years from now is future money, and its value is given by the formula. That's the check that comes into us. It's the 400 t plus 1 squared. So it is a future value from the perspective of 0. And then e to the negative r times time. So we're just putting e to the negative still 0.04. And then the time period now, from the perspective of 0, what represents how much time has passed? It's t. That's why this guy is a t, whereas from the perspective of the end of the experiment, the future value of this, how much time is left for the thing to grow, is 10 minus t. Right? So there's just this fundamental difference in the power, and that's pretty much the only difference in the two formulas. So that is just times t. And so the present value actual, again, converts to an integral. Still 0 to 10, both. Okay, so somebody will type that in for us. Anybody have the first integral for us? Okay, and I always like to make sure, I mean, that 200,000 sounds like a very big number for our tutoring business, but don't forget that 10 years down the road, we calculated the value of the stream. Anybody remember it, or go back and look? It was 48,000 per year for that, for the 10th year. We didn't make 48,000, we made a little bit less in that 10th year, but anyway, you had 10 years of growth, 10 years of money that was coming in at more and more rates, plus you were investing it. So 200,000 seems feasible. Okay, and then anybody have this number for us here? Okay, while we're waiting for, what's that? All right, so while we're waiting for that number, given that we just calculated the 198,000, there's a non-calculus way, far easier than we did here in red, to get this red answer. Because you already know the future value is 198,000 10 years away. That's now a pre-calculus question. We're going to answer it in a calculus way, and we're going to get the right answer. But just as well, we'll do in purple here, or let's just use our pre-calculus formula. The pre-calculus formula is this first guy in red. We know that the present value is b e to the negative r times time. How much is b, which represents the future value at the end of the 10 years? That's the 198. Times e to the negative r times time, so that's a 0.04, and how much time? 10. And you're just going to type that in one shot compared to the integral over here. So Dave, do you have this integral number for us? 133151. Okay. And did anybody try typing in the other one? Or you could just trust me. Oh, it worked. Okay, good. That's comforting. All right, so those are our, that's the present and future value business, right? And it should like be to the penny. We're not even talking like round, like any rounding would be because the, is it 20 cents off? Well, okay, all right. Yeah, so bring the decimals in, and in fact, I stopped writing when Trevor stopped talking at 32, but there were a few more digits there. So if you include all the digits, it will match up perfectly on the calculator. Yeah, and so so I always think of this whenever I hear of like a kind of a startup company that seems to have built some momentum and then gets out bought out for like $1 billion by some massive company. And so how can you value, like, I don't know, Google just bought, Google's always buying stuff. What's that thing that Google recently bought? WhatsApp. So how can you figure out what WhatsApp is worth? It's this. It's you make your best guess for the formula, like the tutoring formula. And then you say, okay, I think WhatsApp is going to be hugely popular for, say, 5 years. Assuming the tutoring formula, put it 5 years out, we can figure out what it would be worth 5 years in the future, which means we can figure out what it should be worth today. And that's the calculation to decide whether or not to sell. Any questions on this one? Okay, so why don't we have you guys now work in your groups with the rest of the activity. There are 3 problems remaining, and I will give you a big hint. One of them is just a pre-calculus question, and using calculus is going to give you, it's just not the right tool. So don't force the calculus solution to all of those problems. One of them is a pre-calc, just to make sure that we are looking for the difference in the setups.